or an exponential equation, I think just the way they appear to us, you know, I see something like those, and it makes me uneasy. I'm uncertain, okay? Don't allow that to kind of creep into your mind, okay? Understand that it's like any other equation we've ever come across, and we are going to basically use the inverse operations to isolate variables, okay? You know, if I had x squared is equal to, 15, okay, I'm going to use inverse operations to help me solve for x, right? Okay, if I have 3x plus 12 is equal to 41, I'm going to use inverse operations to isolate my variable x, right? If that's all we do throughout solving equations. So that's what's going to happen here when we start dealing with these types of equations, okay? So the first ones that we're going to deal with are the exponential equations, okay? Exponential equations. And I want to show you two ways of solving an exponential equation, but then kind of lean usually towards one method because I think it's a little bit more obvious to use that method, and it turns out to overall just going to be easier. But it says an exponential equation is one in which the variable occurs in the exponent. Obviously, that's something if we know what an exponential function is, hopefully we realize what an exponential equation looks like. So some exponential equations can be solved for pretty easily if they're in what we call a one-to-one relationship, okay? Meaning that if they both have the same base, in order to make the left-hand side, okay, if those two things have the same base A, to make the left-hand side identical to the right-hand side, don't the x's and y's have to be the same? Okay, so if I start off with something like that, this arrow says it implies x is equal to y, okay? Or if we write it this way, we could write this as if a to the x equals a to the y, then x equals y. And that would then be the result or the concluding equation that we solve, okay? That's the most simplistic way of solving and dealing with exponential equations. So if you were to see, and you've seen these before, you've seen one-to-one relations before. If I say 2 over 3 is equal to x over 3, do you see that the denominators are both identical? So the only way that this side is going to equal this side is if the numerators have to be the same, right? So what equation do I get? X is 2, right? Or if I had something like this, I would have x plus 2 is equal to 2. The only way that I can make these two things equal is if the numerators equate because the denominators are already the same, right? So that's a situation where you've already seen one-to-one equations in the past. But now with exponentials, it'd be something like this. Let's say I've got 3 to the 2x is equal to 3 to 16. Okay? The bases are identical, right? So in order to make these things the same, the 2x has to equal 16. The exponents have to be the same. Does that allow me to solve for x now? Divide both sides by 2. X is 8. And that should make sense then when I put 8 in here. 3 to the 2 times 8 is 3 to 16. All right? That's a very, very simplistic type of exponential equation. Not all of them look that way, and a lot of them don't look that way. Okay, but it is an option for us if we can recognize that. So if I look at these equations, none of these on the left-hand side or the right-hand side have the same base. So initially people think, well, I can't do that then. What is my attack or attack that we're going to use for these? Okay? Before you start doing anything on any exponential equation, you want to think about, can I rewrite, using my laws of exponents, manipulating my laws of exponents, can I rewrite the left-hand side and the right-hand side so that they have the same base? If I look at 5, and I look at the number 625, is there a relationship between those two? Yeah, what is 625? How can I rewrite that so it has a base of 5? 5 to the 4th. Okay? Because 625 is 25 squared, isn't it? And 25 is 5 squared. So then give me 5 squared squared, which is 5 to the 4th. Okay. And then the left-hand side, obviously, I don't need to manipulate that one because it already has a base of 5. So now we use our law of exponents to adjust these equations so that the bases are identical, and we can solve then by stating 3x minus 2 is equal to 4, 3x equals 6, x has to be 2. Okay. Obviously, then, if you plug 2 back in, you should be able to get a true statement, right? 5 raised to the 6 minus 2 is 5 to the 4th. Well, we have already said that 5 to the 4th is equal to 6.5. So we know that then is the only value that x can be, so that's an equal statement or true statement. All right? Okay. Now, what I show you towards the middle of class, when we start actually using logarithms to help us solve exponentials, we use the inverse operations. This question could be solved using those as well. Maybe we'll come back and solve this equation using logarithms and see that we get the same value too. Okay. If I look at the middle one there, okay, now I'm not, in the first one, that 5 was static. That 5 didn't have to be changed. Here, is there any way that I can change 32 so that it has a base of 8? Meaning, are there any powers of 8 that will equate to 32? Any, I guess when I say any whole number powers. So I say 8. 8 to the first is 8. 8 squared is 64. I missed 32, right? So I can't rewrite the right-hand side of the base of 8, okay? So then the question is, well, what do I do? Okay? If I look at 8 and 32, do they have something in common? They have 2 in common, right? I can take the 8 and rewrite it as 2 to what power? 2 to the 3rd. I can take 32 and rewrite it 2 to the, anybody know that? 5th, 2 to the 5th. 2 to the 4th is 16. So I got 2 times 2 times 2 times 2 times 2 will give me 32. So that's the approach. We're going to try to figure out if I can rewrite both of these so that they have the same base. So 8 is the same thing as 2 cubed. Okay, but we need 8 raised to the 2x. Does that make sense to everybody? So we still have that. And now 32 is 2 to the 5th. All right, what do I do with a power raised to a power like that, 3 raised to the 2x? You multiply them. So I actually have 2 to the 6x is equal to 2 to the 5th. Do you see now, through the manipulating of our base and using our exponent rules, we do now have the same base on both sides? We now developed a one-to-one relationship between the bases, so then 6x has to equal 5. X is indeed 5/6 then. Okay. And if you plug that in, obviously, 5, 6 times 2, okay, is 10/6, right? 10/6 reduces to 5/3. I'll take 8. Take 8 and raise it to the 5/3. It spits back 32, right? Okay, and that's what we were looking for. So, like any other equation, once you find x, plug it back in. See if you get your statement. Okay. The one on the right, e to the x squared is equal to e to the 16th. So what do I write here? I've got e and e. The bases are the same. So can't I say that those two things are the same? All right. So when we do this, you might generate other areas of algebra or equations that address other areas of algebra other than multi-step equations, right? Here you get a quadratic, so you have to factor. If you get a cubic or a quartic or a quintic, you might have to use P over Q stuff. Does that make sense? Okay, so as we use these new procedures, they might generate algebra that targets other solving techniques. Okay, and mainly as we move on, you're going to see it targets a lot of factoring. Okay, so x is going to be what here? Plus or minus 4. Okay. Now I want to show you. So if I'm raising something, even though e is a relatively small number, I raise it to the 16th power. I get something very large, right? Okay. I raise anything to the 16th power is going to be kind of a nasty value. So we did this last period. It took a little bit of time to zoom in and out, but I do think it's important for you guys to see. If I were to take e raised to the x squared, that's that curve there. Okay. I'm going to also then take y equals e to the 16th. Okay. So that is it. You see here, e to the 16th is a very large number, right? Okay. We're up to 8 million, 8.8 million. If that's the case, just like any other equation, the left-hand side is a curve, the right-hand side is a curve, right? Our solution to that equation should be where they intersect, right? The x values which they intersect. If I take and adjust my window here, and this is going to just take a little bit of time, bear with me. All right, so zoom out far enough, we start to see the e to the x squared curve showing up. You see that line here. Pretty soon there's that line, right? Does that make sense? I'm going to zoom back in on that. Okay, so that's what we're looking at. We're looking at those two intersection points, which would be intersection of that and that. You see one of them is at 4, and then the other one there is at -4. All right, so we can do that. Now, here's the thing. Those numbers are so large, a lot of your calculators that you're using are not going to be able to deal with that number. Does that make sense? I don't know what your TIA3 or your 4 is going to mess with or be able to kind of negotiate. But if I was to try to set my window up or zoom in and out on that with my TIA3 or A4, that's going to be kind of a tedious process, okay, if it's even something we can do. But I do want to show you those relationships, even if we go back to that first one where we had, 5 raised to the 3x minus 2. So my hopes are you realize that that is just going to be, our traditional exponential, okay? The parent function is 5. The 3x minus 2 is going to do some type of transformations to that curve. But then when we want to see when does that equal 625, okay, and we zoom out then, we should be looking then at, okay, so we're looking at where that black line intersects my curve, and you're seeing that happens at an x value of 2, right? So that's basically all we're doing, just similar to what we talked about that on the first or second day of class, okay? And when we're dealing with an equation, the left-hand side of the curve, right-hand side of the curve, and the solution is the x value in which they intersect. So those are kind of your easier exponential equations to solve, when you can manipulate the bases so that they turn into the same, okay? Now, and I deleted this on accident, so let me see if I can, there we go. Guidelines for solving just your general exponential equations, okay? First, you're going to isolate the exponential expression on one side of the equation, okay? So you're going to try to isolate your base and its exponent, and that exponent is going to have the variable in it, okay? You're going to isolate that, just like you do any other equation, right? If I'm taking, the square root of x plus 4 is equal to 20, I need to isolate the square root before I start using inverse operations, correct? Okay. So that's the first thing we do, isolate that. Second step says take the logarithm of each side, then use your law of logarithms to bring down the exponent. Okay. So your logarithm is going to be necessary here because that's the inverse operation, and we're going to use that log of a to the c is equal to c times log of a, right? That's the last property, last law we talked about last week. We're going to use that to help us, okay? And then we're going to solve for the remaining or leftover variable, okay? I want to show you an example where you can actually address this two different ways, and you might get two different looking answers, but they are indeed 100% the same. So I'm just going to give you an exponential here that, and I'm not going to use those guidelines first, but because I want you to see maybe the benefit of having those guidelines. Let's just say I have 3 to the x plus 2 is equal to, let's just do this, 3 to the x, go 2x is equal to 10. I think that's what we did last class. 3 to 2x equals 10, okay? There is an exponent that I can raise 10 to so that I get 3. It's just not common knowledge, right? That makes sense? Obviously, hopefully you look at that and you say, okay, well, if x was 0, I'd have 3 squared, right? If x was 1. If x was 1, I'd have 3 squared. And that gives you 9, correct? So does it make sense that x is probably a little bit bigger than 1? Okay, if x was 2, I'd have 3 to the 4th, which 3 to the 4th is going to give me, anybody know 3 to the 4th? 81, okay? So my x value is going to be between 1 and 2, and it's going to be a lot closer to 1 than it is to 2, because 2 got me to 81 pretty quickly, right? So that I think that's a good thing to think about if you can, before you even do the problems. Now I have an idea, I have an estimate of where my answer should be. So if I get an answer of like 41, I know I've done something wrong, correct? Okay. So you can use one of two approaches. Obviously, one of them being those guidelines that I just wrote down for you, just showed you. Or you can use this. You can say that if a to the y equals x, then log base a of x is equal to y. That's your definition of a logarithm, right? Right now, I have something in that form. So let's rewrite that as a logarithm. If I rewrite it as a logarithm, I'm going to log base 3 of 10 is equal to 2x, right? Does that make sense? Did that just give you an equation in which you no longer have exponents and variables and exponents? Can I solve for x? Okay, so I divide by 2, right? Just for convenience sake, and what I want to demonstrate here in a minute, I'm just going to multiply by 1/2. Okay, and if we went to our calculator, maybe I'll show you how to do this on the 83 or 84. I'm on the 83 or 84. What I would do is I would take 1/2 times my, you got to go to, I think most of you, if you have this calculator, are probably going to do it this way. So go 1/2, and then math, go to log base. Okay, so my base is 3. My argument is 10. Okay, hit enter. It gives me that number right there. So now if I take, I'm going to store that as x. So now every time my calculator sees x, that's the number it's going to put in, right? So now if I go 3 raised to the 2x, hopefully spits back 10, and it does. Okay, and that number 1.04 kind of confirms our initial prediction that our x value was between 1 and 2, right? But closer to 1. Now, let's do it using those guidelines that I showed you. And I think this is actually the way that I'm going to predominantly use to solve equations that are exponential. It said isolate your exponential. Okay, well, in this one, that's already done. Okay, but what they're saying is if you would have had like plus 2 is equal to 12, to isolate the exponential, we're going to subtract 2 from both sides. Does that make sense? Okay. So we got that. All right. So the first part said isolate the exponential. The second part said now use logarithms to bring your exponent down. And this is the logarithm rule that we're going to use. If we have the log of some base, I don't care what base, of a to the c, doesn't that turn into c times log of that base of a? That's what we're going to use here. I'm going to take the log of this side, and I'll take the log of this side. Okay? Because I can do it. I can do an operation to any equation I want to, as long as I do to both sides, right? So I take the logarithm of both sides. Now, that allows me to take this, that's the c term, that can come out front, correct? So 2x log of 3 is equal to log of 10. Now, just remember that log of 3 is just a number, right? 2 is just a number. 2 and log 3 are being multiplied together with x, right? Okay, they're just, log 3 is obviously an irrational number, so we don't write it out. We use the symbol log 3 to do that. So this is really x times 2 log 3, right? Does that make sense, everybody? So can I divide both sides by 2 log 3? So I have log of 10 divided by 2 log 3. Okay. Now, just for convenience sake, you wouldn't normally do this. Normally, you'd be done. But I want to compare that to what we did over here and see if we get the same thing. So I'm going to factor out a 1/2. Factor out a 1/2. Now I've got log of 10 divided by log of 3. And my question to you is that the same? And I guess the quick way to check to see if that's the same is just to grab my calculator and say, if I take 0.5 times log of 10 divided by log of 3, do I get the same x value of 1.0479? And absolutely I do, right? So the argument is, why are these two things the same? Why are those two things the same? Do you guys remember from Algebra 2 a phrase called change of base? Okay. The change of base formula says if I have log base A of x, okay, if I want to change the base of that, I can do that, but it's going to turn into log the base that I want to change it to of x divided by log the base I want to change it to of a. And now think about what happens over here. This is log base 10, right? On the right-hand side. That's a 10 right there. It's common log. Okay. So that would be the base that I want to change to. Okay. That's kind of in this format right here, correct? So this one here, if I take that, so that 3 is this A right there. That 10 is this X right here. Does that make sense? So if I take log base 3 of 10, and I want to rewrite it so that the logarithm has base 10, so base 10 is what I'm looking for. Change of base says that 10 is your numerator, and this base becomes the argument in your denominator. is that right there the same as that right there? Yeah, okay? So when you decide on which approach you're going to use, that might dictate the version of the answer that you get back. Does that make sense? All right, if I'm working on this and my neighbor got 1/2 log 3 of 10, and I got 1/2 log of 10 divided by log 3, we're comparing our answers, and we say we're completely different. We've done something wrong. One of us is wrong, right? And in fact, you're both right. So understand that change of base being an option for you when you're working with these. Now, I generally will use this technique over here. Okay, that is the kind of the quickest, most efficient as we move through other examples. Okay, but you can use this definition of a logarithm if you like. Okay, so here's what we'll do. 3 to the, we're just going to do a handful of examples here, guys. 3 to the x plus 2 is equal to 7. 3 to the x plus 2 is equal to 7. Isolate the exponential part. Has that already been done for us? Yeah, this is isolated, right? There's no, like, what we mean by that there's no multiple up front. Okay, there's no sum or difference attached to it. There's no quotient over here. Okay, no denominator. So this is isolated. It's all by itself. So once we have that, you can take the log of both sides. Now here's my argument. It doesn't matter what log you take, as long as it's the same one on both sides. So I can take log base 10. I can take log base e. I can take log base pi, log base square root of 1.5 if I want to. Okay, it does not matter. The most two common logs to take of both sides are log 10, log e. Does that make sense? Or log base 10, log base e. So a lot of times I just write ln because it's just quicker to write. So I'll take the log, or natural log of both sides. Okay, so when you do that, then you can use that exponential rule where the x plus 2 can come out front. Now, remember, that's a quantity right now. It's an exponent, right? So when it comes out front, it's a quantity. And you're then left with ln of 3. And on the right-hand side, I don't have to apply any rules there, so it's just ln of 7. Now, you've got two options. You can distribute and solve for x that way, but that's a pain in the butt. Okay, I'm trying to isolate this x, right? So I need to get that x plus 2 by itself first. So what can I do to both sides to get that x plus 2 by itself? Divide by ln of 3. So I end up with x plus 2 is equal to ln of 7 divided by ln of 3. So now how do I isolate x? So subtract 2. And that's what x is. I think if you distributed that ln of 3, you would end up with ln of 7 over ln of 3 minus 2 ln of 3 over ln of 3. And isn't that indeed the exact same thing? I think. Yeah. Okay. It's just, and now they look different. Okay, but this one has that factor of 1 over here, so we cancel that. It's just that minus 2. Now, if I were to ask you, does that make sense? Is that the number that I have to raise 3 to and add 2 to it to get 7? Well, I'm not sure about that. Okay, so I think the safest thing to do then is to grab your calculator and just check it. ln of 7 divided by ln of 3. Remove 2 from that. I get that number there, right? Okay, store that as x. And then just write 3 raised to the, now when I raise it to the, and I'll do this in, I'll change my mode here so you understand this if your calculator is the most basic. If I go 3 raised to the, and I just type in x plus 2, is that going to do the order of operations the way I want it to? No. Okay, it's going to take 3 raised to the x, evaluate that, and then add 2. I don't want that. I want x to have 2 added to it right away, and then raise 3 to that sum, and we do then get 7 back. Is this okay? All right. When deciding, what logarithm to use, I just generally use ln all the time, but this is a scenario where it kind of explains or shows you maybe the real purpose of using ln instead of other logarithms, other bases. If I wanted to isolate the e to the x, I got to divide both sides by 3, right? So I'm going to have e to the x is equal to 10 over 3. And now we'll take the ln of both sides. Okay? So that's nice. And now, if I have ln of e to the x, you can blindly just kind of do what we've done. Okay? Well, I can use the exponential idea that x is going to come out in front. Okay? The exponent law for a logarithm, so x comes out in front. I have ln of e is then equal to ln of 10 over 3, right? And now what would I divide both sides by to get x by itself? Ln of e, so I'd have ln of 10/3 divided by ln of e. Is that okay? We isolated x, right? Here's my question to you. And that follows suit with the last question. Hopefully the procedure wasn't anything that was taxing. But if you ended up with an equation that said, I go 2x is equal to 4, and you got x is equal to 2, would you divide either side by 1 again and get x equals 2? You want to do that there? We did it over here. What's ln of e? It's 1. Okay? Remember those 4 properties I told you last week? If we had ln of e, that is the same thing as log base e of e. Well, what do I raise this base of e to come back and get that e? It's 1, right? So that's the benefit of using the natural log, is a lot of times we get ln of e's, and they just go to 1. So I have 1 times x, right? Does that make sense? Or you could have done this. You could have known that one of these rules last week looked like this. It said the log base a of a to the x is just equal to x. Well, when I go ln of e to the x, that is this rule here. It says log base e of e to the x. What do I raise e to get e to the x? Just raise it to x, right? So you automatically know that when I take the ln of that side right there, everything vanishes except for just the x, and that's what I'm left with. Is that all right? That is something that you'll use a lot in calculus to kind of simplify a lot of your equations that you're messing around with in calculus. We'd like to see that property be used. All right, let's skip that one. Let's do this one. It's a little bit more complex, okay? Because the process of isolating the exponential is a little bit harder. First thing we have to do is get rid of the fraction, right? Okay, just like always, get rid of that fraction. So what do I need to multiply by so I get rid of that fraction? Yeah, multiply by that denominator, okay? So multiply by that denominator, I get 50 is equal to 4 times 1 plus e to the negative x. Okay? Now, how do I start isolating that exponential? I want to isolate this, right? So I got to isolate the quantity that's in first. Divide both sides by 4, right? 25 over 2 is now equal to 1 plus e to the negative x, right? Now what? Subtract 1. So it's going to give me 23 halves. It's going to be 23 halves is equal to e to the negative x, right? Okay, I've isolated the exponential part. Now do what? Once you isolate the exponential, take the log of both sides. So I have ln of 23 halves is equal to ln of e to the negative x, right? When I take the ln of e, raise the sum exponent, that's going to give me that exponent. So that right-hand side just turns into negative x. And again, that's using the fact that ln of e to the x by one of those properties we talked about, and it's because of the definition of a logarithm, ln of e to the x is just equal to x. A lot of times when you get to calculus, we'll do this. We'll say ln of e to the f of x. So what they're saying is that this thing could be a function. Okay, it could be anything. It could be x plus 2, it could be x plus 3, it could be negative x. What you're left with then is just f of x. Does that make sense to everybody? Where this thing here is no longer just one variable, but it could be an expression or whatever. Okay? So that's what we're left with here, negative x. So can't I do that? And that's my value for x. You could plug that back, save a little bit of time. I'm not going to get to the calculator and plug that back in, but you could do that. You could evaluate that, sort as x, and then type in 50 plus the quantity of 1 plus e to the negative x, or divided by 1 plus e to the negative x, and you'll evaluate that out to give you 4. That's something we can do? All right. I want to get to, there's a couple here we might come back to if we have time at the end of the day tomorrow. You start to get equations like that, e to the 2x minus e to the x minus 6. If I look at that, it's a trinomial, right? And it's of quadratic form. Okay, so we can factor this thing using our quadratic techniques. Okay, something like that. We can do the same thing with. If we have time tomorrow, I'll come back to those. Those aren't kind of the paramount type questions I want to talk about right now, though. I want to deal with just the general types of exponential and logarithmic equations. So now kind of jumping into logarithmic equations a little bit for the next 5-6 minutes. We have logarithmic equations that are one-to-one as well. If you have log written on both sides of your equation, log written on both sides of your equation. So this is saying if you have something like log base e, I don't know e, let's go 3 of x is equal to log base 3 of 12. What this is saying, because the bases are the same, in order for this to be a true statement, in order for this to be an equality statement, doesn't x have to be 12? Okay, so this rule here is saying if you have the same basis, okay, log on the left-hand side, log on the right-hand side, then to make that a valid statement, to make it a valid argument, is that your x and your y, or your two arguments, have to be identical. Okay, so if this was, log base 3 of x plus 2 equals log base 3 of 10, I just say x plus 2 is equal to 10. X has got to be 8, right? That's the only number that I can make plugged into here that it's going to give me the same argument that I have over here. Those are your one-to-one equations. Those are pretty easy. Kind of see them here, though, this one. It's the same idea. Okay? Doesn't the bases are the same? Doesn't 4x have to equal x squared? Okay? Here's the thing. When you do these, you might generate other algebra that we've talked about throughout the year. I don't always get one-step, two-step, three-step equations, right? I might get something like this. And when I have x squared, I have to do what? Whenever you have an exponent that's greater than 1 in your equations, the general process is to starts with an f and ends with after. Okay? Right? Okay. So we're going to get this 0 equals x squared minus 4x, right? That factor to x and x minus 4. How many answers do I get? 2. X equals 0, x equals 4. You might get multiple solutions, okay? However, when you get multiple solutions, you should do this even when you get one solution. You got to check them. Plug 4 back in. What's 4 times 4 in that first logarithm? 16, right? Okay. So log base 2 of 16, does that equal log base 2 of x squared? What's 4 squared? 16. So log base 2 of 16, does that equal log base 2 of 16? Yeah. So then I think, okay, let's plug 0 in. Let's plug 0 in on both sides, I get 0, right? So we get log base 2 of 0 equals log base 2 of 0. That makes sense. That's identical, right? But we're saying that there's some number that when I raise 2 to it, I get 0 back. What number would you raise 2 to so that you get 0 back? If I raise 2 to the 0, don't I get 1 back? Okay, so 2 raised to anything bigger than 0 would give me a number bigger than 0 back. And 2 raised to anything less than 0 is going to give me a number actually bigger than 0 back as well, right? So there's no way that I can plug 0 in. Okay, when I say log base 2 of 0, 2 to the what gives me 0, there is no value for that. Anybody know why? Graphically, what is x equals 0 for a logarithm? Vertical asymptote, right? Okay, it's not part of our domain. And those are things you have to think about as you're getting solutions. That's the easy thing to do is to check with your calculator. If I take log base 2 of 0 on my calculator, it's probably going to tell me we've got a problem. We'll see what the GeoGebra spits back negative infinity, which is a problem. But if I type in, let's go to math, log base. So I want log base. This one you got to talk about putting it in backwards. So this is the argument. That's the base. Hit enter. See how it says error domain? Okay. That's telling me that you cannot use 0. Tomorrow we'll start here. Basically just the guidelines for solving logarithmic equations. If you got log on both sides, we just talked about how we do that. It's usually a 1-to-1 comparison. If you only have log on one side, you need to isolate that, just like you isolated the exponential. Okay? Then what you're going to do is you're going to use the definition of a logarithm to convert your equation into an exponential. Does that make sense? And that should then bring out that variable argument and allow you to solve for x. Okay? So just like any other types of equations we've dealt with and that we'll ever deal with, if I want to solve them, I have to understand their inverse operations, their inverse functions. Okay? Exponentials and logarithms undo each other, right? So they're going to be the inverses that we use inside equations to solve for variables. We'll get through 4 or 5 examples of those tomorrow, and then start to apply these to our continuous compound questions and our our monthly, yearly, those types of compound questions. All right? Maybe do a couple of half-life questions as well tomorrow, because on your final there is a half-life question. Okay, that's the plan. Remember, there are some assignments that are open, but the system equations and all the conic sections are not due until after Christmas.